Good afternoon, everyone. Thank you for being here. My name is Kamran Aghaee, a postdoc at Cornell University. Today I'm going to present part of my PhD research on shrinkage reducing admixtures and shrinkage mitigating materials, which was done at Missouri University of Science and Technology under Dr. Kamal Kayat's supervision. The title is Microstructural and Thermodynamic Analyses Elucidate the Effects of Expansive Agent and Shrinkage Reducing Admixture on Performance of Fiber-Reinforced Mortar. Here you see the outline. I'm going to start with the investigation method. We'll talk about the experimental method, discuss the results, including mechanical and shrinkage properties, microstructural analysis, thermodynamic analysis, and finally we'll wrap up with some conclusions. Mechanical and shrinkage properties included compressive strength, fiber pullout, and shrinkage. Microstructural analysis included XRD, TG, MIP, SEM EDS, and microindentation to measure the effect of shrinkage mitigating materials on microstructure of fiber-reinforced mortar. Thermodynamic analysis was done to predict the phase assemblage, compressive strength, and chemical shrinkage of fiber-reinforced mortar made of shrinkage mitigating materials. So the shrinkage mitigating materials I'm talking about are these materials: expansive agent, which induces initial expansion, which compensates for the later age shrinkage. The specific type I used is a CaO-based, which its hydration product is potendite, and it induces initial expansion, as you see on the right, and reduces the later age shrinkage. There are different types of expansive agent, MgO-based and CSA-based, which I use the CaO-based. Shrinkage reducing admixtures are non-ionic surfactants, which reduce the surface tension of the pore solution and reduce shrinkage. You see the mixture matrix on the table. I use high content of expansive agent and shrinkage reducing admixture. Expansive agent was used at 10%, substituted by weight of cement, and SRA 2% of the cementitious material and substituted to water. Water to cementitious materials ratio was 0.4, and steel fiber was 0.5 of the volume of concrete, and aspect ratio of the fiber was 65. You see in the middle the compressive strength and fiber pull-out strength testing process and equipment. On the right, I use embedded strain gauges, which enabled me to measure the shrinkage immediately after casting while the concrete was fresh and up to the end of the experiment. Compressive strength and fiber pull-out strength results are shown on the left plot. As you see, using the shrinkage mitigating materials led to the mechanical properties reduction, and the highest reduction was when I used them in combination. 18% for 28 days compressive strength and 29% for fiber pull-out strength at 28 days. However, as you see in the middle, they were so effective in reducing the shrinkage. Initially, within 10 hours, they eliminated shrinkage, and even after 12 hours, 100 microstrain shrinkage was obtained. After 28 days, some mixtures, those including the expansive agent, were still in slight expansion, and overall, I observed a very significant effect of these materials on shrinkage. TG, XRD, and MIP was done On the left, you see the plot showing the different phases decomposition at different temperatures. And for example, potentite CH was decomposed at around 400 degrees centigrade. And the highest, as you see, was for the EA mixtures, due to the highest high portlandite formation into the matrix. XRD result in the table, as you see, confirm those results, and however, the lowest portlandite content was for the SRA mixture, which was due to the delay in hydration and strength development, which is aligned with compressible strength development. The unhydrated C3S and C2S content was the highest for SRA due to the same reason. On top table, you see the MIP result. The highest total porosity was associated for the EA mixtures again, and highest macro pores as well. On the other hand, the highest gel pores were found for the reference and SRA mixtures, which these results can confirm the strength development and shrinkage behavior, which I've already talked about. I did SEM EDS pointer scanning in 2 strips, as you see on the left image, up to 100 micron away from the fiber, and 100 points in each strip were scanned. And as you see, Psi to CA ratio over 0.4 indicates the presence of CSH into the matrix and denser matrix, longer silicate change, and enhanced hardness. On the other hand, lower Psi to CA, lower than 0.4, indicates the presence of potentite, stringite, and monosulfate in the mixture, and lower quality of the microstructure. Higher points over 0.4 Psi to CA over 0.4 was found for the reference mixture, indicating the stronger matrix compared to the other mixtures. In addition, in the secondary region, more points with higher Psi to CA ratio over 0.4 were found, again indicating a stronger matrix away from the fiber. With the same logic, SEM EDS line scanning was done, and the gap between the Psi and CA element was narrow for the reference mixture, narrowest for the reference mixture, indicating the stronger matrix and quality of the microstructure, and wide gap was obtained for the binary combination of the shrinkage mitigating materials and the 10EA 2SRA mixture. This could justify the fiber pull-out strengths, lower fiber pull-out strengths for the 10EA 2SRA mixture. Micro-hardness again was done for the 2 strips, and the overall results showed the descending strengths, and the highest strength was again obtained for the reference mixture, and 10EA mixtures had the lowest strengths. And again, in the second region, except for the 10EA mixture, for the other mixture in the second region, higher strengths was obtained. In addition to experimental study and microstructural analysis, thermodynamic analysis using GEMS or GEMS, which is Gibbs energy minimization, was done. GEMS is based on minimizing Gibbs energy for a complex chemical system, and as you see in the equation, the Gibbs energy is dependent on enthalpy and entropy, and when it's negative or minimum, It's desirable, which indicates the spontaneous reaction, which is the case for cementitious materials, and it's desirable. For this thermodynamic analysis, we needed to introduce the mixture proportioning as well as the chemical composition of the binders obtained from XRD into the software and get the different phases, solid, aqueous, and gaseous phases as the output. Another outputs were hydrates or phase assemblage, degree of reaction of binder, porosity, chemical shrinkage, and pH of the system. GEMS is applicable to both plain binder system, OPC, or blended binder systems. On this slide, you see the phase assemblage predicted by GEMS and highest portlandite formation for EA mixtures and lower CSH compared to the reference mixture for them, as well as higher porosity for the EA mixtures compared to the reference and SRA mixture. Compressive strength and chemical shrinkage were predicted, which especially for compressive strength, there was a good agreement with the prediction and whatever we observed in experimental study and microstructural analysis. In conclusion, EA and combination of EA and SRA eliminate shrinkage after 10 hours for fiber reinforced mortar, which I studied, and those mixtures remained in expansion even after 28 days. That was due to the high content of portlandite formation. A high content of shrinkage mitigating materials, reduced mechanical properties, and EDS line scanning indicated strong fiber matrix ITZ for reference, which implies higher fiber pull-out strengths for the reference. Large gap between the psi and CA with the use of shrinkage mitigating materials indicated lower density and quality of the microstructure. EDS pointer scanning showed that psi to CA ratio reduced with the use of shrinkage mitigating materials, and psi to CA ratio over 0.4 was observed in the secondary strip, and higher points were detected in that region, indicating a stronger microstructure away from the fiber. MIP results indicated higher porosity using shrinkage mitigating materials due to the formation of pores, micropores, and lowest porosity for the reference mixture. Thermodynamic simulation and phase assemblage indicated the high formation of the portlandite and low CSH for the EA mixtures, and although they worked very well in shrinkage elimination, exhibited low mechanical properties. I would like to appreciate Dr. Kamal Kayat's support and supervision on this study, and I acknowledge the valuable collaboration of Dr. Kumar and Han on this research. These are the references, and thank you for your attention. I'm happy to take your questions.